Welcome to another Mount Holyoke Psychology Statistics Hub tutorial. This is your lab director, Natasha, with a new research question for you. Jorge is a campus celebrity, and students love taking pictures with and of Jorge. Does the average number of pictures taken differ based on your class year? So do first years, sophomores, juniors, and seniors take different amounts of photos with Jorge on average? What analysis can you use to answer this research question? The one-way ANOVA tests means of different levels of an independent variable on a dependent variable. You should run a one-way ANOVA when you want to compare means of different levels and groups of a variable on a dependent variable. In this example, we ask, is the average amount of Jorge pictures taken each year different for students who are first year, sophomores, juniors, or seniors at Mount Holyoke? The code for running an ANOVA in R is model, the goes into sign, AOV, parentheses, the dependent vector, tilde factor, comma, and then the data equals the name of your data set. Again, we save this as a model so that when we want to view the output, we can take a summary of the model. So before we actually enter this code into the console, we're going to import our data and make sure that RStudio is reading the factors as factors. So reading class year as factor. Again, in this example, class year is the factor and Jorge Pics is the dependent variable. So we're going to import our data set. When we see the data preview, we see now that the way that class year is written is not as a factor. We need to use the pull down menu and change that to a character. Now, when we see it, we can see that in the preview that it is reading it as a character. That means that it's going to treat it as a factor. So we can go ahead and import our data. Now in the console, we can use the code to run the ANOVA. So again, we're going to be saving this as a model. So we'll say model goes into AOV in parentheses. Our factor in this case is, our dependent variable is Jorge Pics. The tilde sign, and then class year is our factor, and the data set is stats practice. Then we can hit enter. Now that is saved as the model, and now to see the output, again, we'll write summary, and then the summary of the model. This gives us information to let us know that overall the ANOVA is significant because it's less than 0.05. It gives us the degrees of freedom, 396, and it also gives us our F value. So what we don't know is at this point, for instance, it does not give us the descriptive, so the means and standard deviations. So the way to get these is to use the code above in this note that we have here. So we can say by, in parentheses, the name of our data set, so stats practice, $, the dependent variable, so Jorge Pics, comma, the name of our data set again, so stats practice, $, the factor, which is class year. And then first we can find the mean. So we'll type in just the mean and hit enter. That gives us the mean for each of the class years. So 9 pictures taken by first years, 4 pictures taken by sophomores and juniors, and about 9 taken by seniors. We can use a similar code by pushing the arrow button and just changing the mean to say standard deviation, so SD. And that gives us the standard deviations for each of the classes. So even though we have the means and we can kind of guess where the differences may lie, we don't know which differences are significantly different until we run a post hoc test. So finally, we need to run a post hoc test since the test was significant. So in order to determine what type of post hoc we need to run the Levene's test of equality of variances. The code is Levene capital test, and then we'll put our dependent variable, so Jorge Pics, or sorry, the dependent variable Jorge Pics, tilde class year, and then let it know that the data that we're using is stats practice. This tells us with the p-value right here that it is a significant Levene's test. So what that means is that the variances between the groups are not equal. So that violates the assumption that the variances between the groups will be equal. So because of that, we can't use a Tukey or some of the other post hocs that you may be familiar with, and instead we'll have to use one that accounts for the differences in variances. So let's use a Games-Howell. In order to run a Games-Howell test, we have to load the package RStatic. So if we say library and then RStatics, there it is. Now that is loaded, and we can use the following code to run the Games-Howell. Games_Howell test, _Howell_ test. And then in parentheses, the name of our data set. So stats practice, comma, dependent variable, so Jorge picks, tilde class year. And this returns the following output. We can see that all the significantly different pairs are marked with an asterisk. So it gives us the 4 different combinations that are significant. So that means that the variances, the means of the 2 groups of the first years and the sophomores are significantly different. The first years and the juniors are significantly different. The sophomores and the seniors are significantly different, and also the juniors and the seniors. So now that we know that those groups are different, we can scroll back up to the means and say, okay, since we know that the first years and sophomores take significantly different amounts of pictures, we can safely say that the first years take significantly more pictures because they take around 9 pictures a year versus the sophomores that take 4. So you'll need to spend a little bit of time looking through each of these pairs, finding out where the differences are, and just double checking with your descriptives to know what the direction of the differences are. So as the output shows, the first years take significantly more pictures than the sophomores and juniors, and seniors also take significantly more than sophomores or juniors. So maybe the first years are extra excited about meeting our campus celebrity. Maybe seniors are feeling nostalgic and wanting to make memories. We don't know, but that's the way the data turned out. So as always, don't be mean, be above average.